So, for example, let's take the curl of the field that we used for the plotting example. So, say you have f of x, y, and z is equal to x times y in the I direction plus y squared sine of c in the j direction plus 2xc in the k direction. So we want to test if this force field is conservative or not. So we take the curl of f and see if it's zero. So let's take the determinant of I, j, and k of So first you write your partial derivatives at the very top. So this is partial x, partial y, partial c, right? And below you write the components of the force. That's xy. Here's y squared sine of c. And in the last box you write 2xc. Right? So you take this determinant. And just using the formula, then you can say that this is the partial derivative with respect to y of 2xc minus the partial derivative with respect to c of y squared sine of c. And all of this will be in the I direction. Now in the I direction. Now in the j direction, that is along the y-axis, then I have the partial derivative with respect to c of xy minus the partial derivative with respect to x of 2xz. This is along the j direction, plus the final term will be partial x of y squared sine of c minus partial y xy multiplied by the vector along the k direction. Now it is a matter of taking partial derivatives. So let's write the final result of the cross product. So say for example, first we take the derivative with respect to y of this term, and clearly since there's really no y involved in the derivative, then the first term of course is going to be 0, and then you have to subtract the partial derivative with respect to c of, say for example, this term. Now this term, the partial derivative with respect to c, you take it as a derivative such that everything that is not c is a constant. So y squared in this case is a constant, so you can take it out. There's no problem. Y squared, and then the derivative of sine of c is, well, cosine of c. So this is y squared cosine of z in the I direction. Now we go to the j direction. Now in the j direction, you have to take the partial derivative with respect to z of this component, and this is of course 0 because since there is no z. And then you must take the partial derivative with respect to x of this function, right? And this function, of course, there's an x there, so there's a non-zero derivative, and this will give you 2z, sorry, because we're taking the derivative with respect to x, not with respect to c. So this would be 2c in the j direction, and then you must take the derivative with then for the k component, then you take the derivative with respect to x of this function, right? And this is pretty much a 0, and then you subtract the partial derivative with respect to y of this term, and that turns out to be x in the k direction. So once you gather all the terms, then you see that the curl of F is going to be equal to minus y squared cosine of z in the I direction minus 2z in the j direction minus x in the k direction. And this is the curl of this function. And since it is not zero, this force is clearly not conservative. So now you ask the question, well, why is this important? Why is all of this important? Why is, knowing all this is important? And well, it's because it's related to the principle of conservation of mechanical energy. To the principle of conservation of energy. And pretty much we know that if, mathematically speaking, that if the curl of a vector field is zero, then this implies that F can be written as the gradient of some function that I call the potential energy function. And it is important to notice that if I take the curl of this function, then if you do all the procedure, then what you will get is that this would be the partial derivative with respect to c, partial derivative with respect to y, minus partial derivative with respect to y, partial derivative with respect to c of the potential energy function, say for example in the I component. And this quantity is going to be, well, is going to be 0. Why is it 0? Because we are assuming that these functions satisfy the property that the order of the partial derivatives do not matter. That is, that the partial derivatives are commutative. That is what we say. And before looking at the principle of conservation of energy, then it is important to look at an example of how all of this works. Of course, I have only just done, for example, the ith component, right? So this is kind of like the x component. If you want to just delete this unit vector, this is what you would get. But you can do is the same for the y and z components, and notice that you will just get cross derivatives and flipped derivatives, if you will, and then all of these terms will go to 0, and will tell you that effectively this is the curl of the gradient of a function is of course 0. Now, so before looking at the principle of conservation of energy, let's look at an example. So let's clear here the board, and let's start with the example. So the example is really simple. We're gonna look at a very familiar force field, that is the gravitational field near the surface of the Earth. So say we have a force field that's equal to F equals to mg in the j direction. Actually, let's do it in 3 dimensions so that that it's a little bit more clear what I'm doing. So this is in the k direction, and I want to, well, first of all, prove that this is a conservative force. Then I want to say, well, from the force, obtain the potential energy, right? So that's one of the very important things that you must learn how to do. And then from the potential energy, find the force. Okay, so it's very, very, very important to know how to do that. And so let's look at the solution. So part A, is this a conservative force? So the test we already know about is take the curl. And if we take the curl of this function, then we would have to do the curl of f is equal to the determinant of I, j, k of partial x, partial y, partial c of, well, there's no force in the x direction, so we can write it as a 0. No force in the y direction, so again, we can write it as a 0. And there's a force in the k direction, that's minus m times g. That's how this force is represented, or how we wrote this force, right? And so let's take a look at this. So this is the partial derivative with respect to y of minus mg minus partial derivative with respect to z of 0 in the I direction, plus then comes the partial derivative, to be consistent, with respect to z of 0 minus the partial derivative with respect to x, with respect to x of minus mg in the j direction, plus partial derivative with respect to x of 0 minus partial derivative of y with respect to 0 in the k direction, right? So that's how you take the curl of this vector field. And as you notice, this is pretty much a constant force. And so we say that the curl of f is equal to 0, and thus we get that this is a conservative force. A conservative force that, I mean, we already knew this all along from our high school and from our introduction to physics course, so it should not come as any surprise. Now for part B of the problem, we shall use the definition that this potential energy function is equal to the minus integral from of f dot ds, right? And again, this minus sign is very important when defining the potential. And so we say that phi is going to be equal to the integral from some initial height 0 to some point c, right? Since we know that this is not this force is conservative, it does not depend on the path we take. So we're gonna, and since this force only depends on the height along the z direction, as you can see, then doesn't really matter what path you take. So you can just use the an integral from z, and we're gonna start our trajectory from some height h0 above the ground to some height h. It can be above or below. Actually, z gives us the sign, and always remember the negative sign in front of minus mg, right? And I should put this, use this as a vector. That's very important. So this is in the k direction, right? And I must dot product it with the path, and the path I'm going to take is upwards. So any displacement upwards can be labeled, or in the upward downward direction will be labeled by a dz in the k direction. Now this displacement can be positive or negative. This is given by the integral, by the limit in the integral, and you can say that since mg is a constant, that this is equal to mg, both negative signs cancel, of the integral from h naught to c of dc of k dot k, right? And since k is a unit vector, this will always be equal to 1. And so we know that phi is equal to mg multiplied by the integral from some arbitrary height h0 to a point z of dc, and then you know that then the potential energy function of x, y, and z of the gravitational potential energy near the surface of a planet is going to be given by mg z minus h0, right? So very, very simple, very, very straightforward, and this you again already know from your or should already know it from your introduction to physics 1 or basic physics. And so now this is part B, and from part B then we're gonna get the solution to part C. So for part C of the problem, we are asked to find the force given the potential energy function. So for our gravitational potential as a function of x, y, and z, we found that this was given by mg z minus h0, where h0 is some arbitrary constant. And once you choose your constant for a problem, you must keep it like that for the rest of the problem. And so from the definition of the force, at least for conservative forces, this force is equal to the minus gradient of the potential energy. Now remember that this gradient function is going to be equal to the partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to c, and you must take it with this partial derivative of the potential energy function. So this is the derivative of this expression, and you can write it this in several ways. So you can write this as minus the gradient of the partial derivative with respect to x of mg z minus h0, comma, partial derivative with respect to y of mg z minus h0, then partial derivative with respect to z of mg z minus h0. Guess you can just take this excess parentheses off. Let's write it in a more consistent way. So this is of mg z minus h0, and be careful to close all your brackets, and then you start taking the partial derivatives with respect to the different variables. So say for example you want to take the partial derivative with respect to x of this term, then since there are no x's in the expression for the function, then this is 0. Then we go to the y component, and you see that the y component of the force is also 0, since the partial derivative with respect to y of this expression it's also going to be 0, since there are no y's. And finally, we must take the partial derivative with respect to c of this component. And for this component, you notice that the partial derivative with respect to c of z is 1 minus the partial derivative of this function with respect to c of h0. And well, since since this is a constant, its derivative is 0. So you can say that the derivative of this term is going to be equal to mg. And thus, if you write the force, the resultant force, this is going to be equal to minus mg in the k direction. And this force is compatible with this other force, and so we are being consistent with our definitions. And that is how you solve for the force given a potential energy function. So now that we know how to get the potential energy function from a conservative force, we can now talk a little bit about the conservation of energy, or conservation of mechanical energy in this case. And so we know for a fact that 1/2 mb final squared minus 1/2 mb initial squared is going to be equal to the integral from an initial point to a final point of the net force of all the conservative forces dot producted with a path displacement. And we must also, for completion, include the work done by all the by the net all non-conservative forces, right? Since this is what we had already discussed. Now, if we look at this term, we really don't know how to write it, so we must leave it as is. But we know for a fact that this is the minus gradient of a potential energy function. And so for this part, I want to focus on this integral. Now, if the force is conservative, we know that F pretty much depends on x, y, and z. So this, you can write it as F conservative of x, y, and z. And then this implies that this potential energy function will also depend on x, y, and z. That's you know how it goes. Now from the integral, we know that the integral from xi to xf of this potential of this conservative forces, right? Conservative forces dot ds. It can be written as minus the integral of xi to xf of the gradient of this potential energy dot ds. That is what we have said. There's nothing new here. But now let me write this in the following way. So using the definition of ds, we can write it as minus the integral from xi to xf of the partial derivative with respect to x of phi dx plus partial derivative with respect to y of phi dy, plus the partial derivative with respect to z of phi dc. Now you say, well, what does this have to do with anything? And is that, remember that we said that the absolute derivative of a function can be written as the partial derivative of x with respect to the function multiplied by x plus partial derivative of y of the function dy plus partial derivative of z of the function dc, right? So this is what you call an absolute differential. And so I can substitute it back, and so I get that the conservative force, or that this integral, right, the integral from xi to xf of a conservative force of the conservative forces can be written as the minus integral from xi to xf of d phi. Okay, so this is the part where it's important to notice that phi does not depend on time. If it depends on time, this is not the absolute derivative, and we cannot say a lot about it. But since it is a potential energy function that does not depend on time, we can do it. And so this is equal to, according to the fundamental theorem of calculus, this is going to be integral from xi to xf of d phi, right? You can write it as a minus of minus phi of x x final minus phi of x initial. And this result is very, 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 very important, since it allows us to write the change in kinetic energy, right? Half m bf squared minus 1/2 m bi squared, as you can already consider this negative sign and write this side as phi of xi minus phi of xf, and you must add the work done by all the non-conservative forces, and this is F not conservative forces dot ds, and so you get that 1/2 m pf squared plus phi of xf, right? You can gather these terms, minus 1/2 m bi squared plus phi of xi is going to equal to the integral of xi to xf of f non-conservative dot ds. And this is what's called the total final energy. This is the final energy, and this is called the total initial energy, and this is what's called the dissipated energy by the non-conservative forces. Now, it is important, let's just make a note here, this is final energy of the system. This is initial energy, and this is dissipated energy. And this is just what's called the principle, and all of these terms is what's called the conservation of mechanical energy. So all of these terms are encompass what's called conservation of mechanical energy. So pretty much it tells you that this difference in energy, so if you take delta E, this is equal to the energy dissipated or energy input in the system, depends on what sign this dissipated energy takes, but this is pretty much the conservation of mechanical energy theorem. And if there are no conservative forces, if there are no conservative forces, then we can say that if there are no non-conservative forces, then of course the change in energy of the system is going to be 0, and so energy final is equal to energy initial, and there you have your conservation of energy principle, the one that you have always been familiar with, and that at least to some extent you should know how to use. Okay, so if you have any questions, please do let me know.